Very good afternoon and warm welcome to this live session. I am Dr. Vaibhav Pandit, and today for the subject electromagnetic field theory we are going to discuss the topic boundary conditions. So this is our 15th live session for the subject electromagnetic field theory. Various topics we have dealt so far to clear the doubts of many of the students. So as our subject electromagnetic field theory is there, basically the study can be divided into the two parts: the study of static electric field and the study of steady magnetic field. Here the topic boundary condition comes three times into the subject. Two times while we study the static electrostatic field, and next time it is for the magnetic field here. So let us have the recap what we have the boundary condition three times, or the three types of boundary conditions into the subject, and then we shall have a practice solving few of the sample problems here. So here we have first of all the boundary that separates the free space from the conductor. So here you just look out. See, this is the conductive material. Whatever the curved line you see, this line separates the conductive material downwards to the free space in the upwards here. Okay, so this is the free space, this is the conductor. So the question may be to your mind that how do you differentiate between the different materials here. See, the differentiation of the type of the material to be a conductor or a bad conductor, it means insulator, all it depends on the three parameters. First one, the conductivity denoted by the sigma, that is mostly we measure in terms of the Siemens. Next to that we have the permittivity of the medium that we denote with the help of the epsilon measured in terms of farads per meter. And the third is the permeability of the medium that we denote with the help of the symbol mu measured in terms of Henry per meter. There is one student, Ashok. Yes, Ashok, if you have any query, you can ask me. I'm just dealing with the three types of the boundary conditions into our subject. The first boundary condition we are dealing the boundary between free space medium and the conductor. Next to that we will have the boundary condition between the two mediums to be the perfect dielectric mediums, but the dielectric constant will be the different from one another, and the third one will be the magnetic boundary condition. So here it is, yes Ashok, for the free space and the conductor. So this is the line that you see that separates the free space and conductor. So I was talking about the three parameters that describe the type of the material, whether it is a free space, whether it is a conductor or non-conductor here. So the conductivity can be denoted by the symbol sigma here. So mostly it is measured in terms of Siemens here. Whereas the permittivity of the medium is denoted by the symbol epsilon, and the permeability of the medium is denoted by the symbol mu here. So epsilon is measured in terms of farads per meter. So I hope you know that farad is the SI system utilized for representing the capacitance here, whereas mu, permeability of the medium, is measured in terms of Henry per meter. So here it is the Henry. Henry is used for representing in SI system of measurement for the inductance here, whether it is the individual inductance or the mutual inductance here. So these are the three parameters: sigma, that is the conductivity, epsilon, that is the permittivity, and mu, the permeability here. So for the free space, most of the times we deal with the two constants, epsilon 0 and the mu 0. Epsilon 0, so we put 0 in the suffix of this epsilon. So the value, the constant value, most of the time you have used while solving the problems related to the electrostatics, mostly in the cases of the Coulomb's law and so forth. So that it was 8.854 into 10 raised to the power minus 12 farads per meter, or sometimes you have used 1 upon 36 pi into 10 raised to the power minus 9 farads per meter. It is one and the same value. Just putting the value of the constant pi to be 3.14, it will give you the other value here. So for free space, the permeability we have taken to be denoted by mu 0 here. So that value it was while you learned the Biot-Savart's law. This was the parameter introduced that time, and it is holding the value 4 pi into 10 raised to the power minus 7 Henry per meter here. See, epsilon is the parameter describing the material, how it is permissive to the flow of the electricity through it, or the conduction of the charges through it, you can say here. Whereas mu is describing the property of the material, how it is permissible to the flow of magnetism through it, and conductivity sigma, better you know the flow of the current. So if sigma is equal to 0, you will say that it is not a conductor, it is insulator, where it is having certain value of conductivity sigma. So you can differentiate it to be a conductor. Now depending on the values, whether we are getting higher values, you will say this is the good conductor, or bad conductor if you have low values. And if it is completely 0, you will say it is insulator here. So these are the three parameters very important to understand while we categorize any medium to be a good conductor or a good dielectric, bad conductor, or completely the insulator. It means the perfect dielectric here. So now free space will be having sigma is equal to 0. Then epsilon 0, the constant value I have just now discussed with you. Mu 0, that is 4 pi into 10 raised to the power minus 7 Henry per meter. So these are the three parameters that describe the medium above this curved line. So this is what the free space here. Whereas for the conductor, sigma will not be equal to 0. See, sigma will not be equal to 0. It will have certain positive value. Then and then only we have the conductivity. And the corresponding epsilon and the mu will of course be there. So this is the first type of the boundary between free space and the conductor. Now with the help of the boundary conditions, what information we are getting, what we are learning in this subject is a very important question. See, whenever we are making the use of electromagnetism for accomplishment of various applications in our world, so that time we need to, for example, take the information coded with the help of the electromagnetic signal, and that you want to transmit from one place to another place. So at one side you will have the transmitter, on the distant end you will have the receiver here. So this signal, the electromagnetic signal, will be going through various kinds of the material media, you can say. So it may be a dielectric, it may be a conductor, it may be a free space. So wireless communication, mostly we are making it possible in the air. So it holds the properties that we have for the free space. Epsilon 0 we have to be the permittivity, mu 0 we have to be the permeability, and conductivity sigma is equal to 0 here. So now in electromagnetics we have the understanding of the four most important quantities, I say, or the parameters you say. So these are the field intensities and the flux densities. So for the electric field, we have the denotion of electric field intensity that defines the strength of the field by capital E. Electric field intensity, that is measured in terms of volts per meter. Whereas for the magnetic field, we have denoted it by the help of capital H in terms of amperes per meter. So I just write here amperes per meter. Electric field intensity in terms of volts per meter. So these are the field intensities. This is for the electric, this is for the magnetic here. Now we have for the electric flux density denoted by capital D and measured in terms of coulombs per meter square. So this is the flux density. Whereas for the magnetic field, we have the flux density, magnetic flux density denoted by capital V, measured in terms of Weber per meter square. Simply the flux is measured in Weber and flux density measured in terms of Weber per meter square here. So these are the four most important vector quantities or the parameters to describe the electromagnetic field behavior. So now as we have the first type of the boundary separating the free space from the conductor. So if there it is a tabletop, the table is made up of a material, metal, so that time it will be a conductive material. And the air above the tabletop is of course a free space. So this is the line for such example, that is a boundary. The line separates the free space medium from the conductive medium here. So thereupon we have to see the behavior of these four parameters, the four vector quantities, while the electromagnetic field signal switches one material and enters the another material here. So in this journey we have to see. So as this is the first boundary between the free space and the conductor, here especially we will be concerning about the quantities describing the electric field only, as we don't have right now any current component. So we are not supposed to see the behavior of H and B. We have to check the behavior of E and D only. So now while the electromagnetic signal is making a journey, let us say from conductor to the free space medium, or from free space medium to the conductor. So as we know the electromagnetic wave, if we have this to be the horizontal line, this to be the vertical line, and the another line. So we have the three mutually perpendicular axes. Electric field, for example, is having the variation like this. Magnetic field is having the variation perpendicular to the plane where the variation of the electric field is going on. So at the boundary or at the line that separates the two media here, it may be a possibility that the quantity, that is either the electric flux or the electric field intensity. So this is normal. The normal means perpendicular to the boundary surface, or it is tangential, or in general if it is like this. So we have to resolve into the two components. So see here, D is representing electric flux density. So the D component can be resolved into the two subcomponents. This is the normal denoted by Dn. So it makes 90-degree angle to the boundary separating the two mediums here, free space and the conductor here. Whereas a dt is tangential. So T, the suffix is referring the tangential component. It is parallel to the plane of the boundary that separates the two free space and conductive mediums here. Whereas n is normal here. So this is resolving the d vector into the two components, dn and dt. Similarly, here it is resolving of the two components for electric field intensity. E can be resolved into en and that of et here. So for the studying of the behavior of the normal components and the tangential components for the electric field intensity and electric flux density at the line that separates free space from the conductor, we have these two differential geometrical shapes here. So whatever the rectangular section you see here, it is just a closed loop here, closed loop. So from any point you start, the path will take you to the same point after a journey, and this journey, half of the journey will be taken place into, let us say, medium one, that it is free space, and the half of the journey, rest of the half, will be conducted into the second medium, that it is the conductor here. Whereas we have here this to be a parallelepiped like structure here. So this is half portion, it will be there in the free space, half portion into the conductive space here. So basically we are having this particular body, a three-dimensional figure here, geometrical figure. So it also holds the surfaces and the volume enclosed inside the closed body here. So the behavior of the d vector and the e vector we shall analyze by just having the integrations here. So for that purpose I have already delivered my lectures, boundary condition between the free space and the conductive material and the rest of the boundaries also. Now here the important points I will just talk about. At the boundary surface, you will come to see that dt will be equal to et, and both the components are equal to 0. So it means tangential component of the electric flux density is equal to the tangential component of the electric field intensity, and both are equal to 0. Whereas dN is equal to, we know the relation, D is equal to epsilon E. So electric flux density can be obtained by just multiplying the electric field intensity by the epsilon here. So epsilon is permittivity of the medium here. So this is equal to rho s here, the normal component. Rho s is the surface charge density. Surface, it means it holds the area, surface area, and the charge, it holds the SI system of unit to be the coulomb here. So coulomb per meter square will be the unit for rho s. It is surface charge density. The 3 points with respect to the boundary that separates the free space from the conductive medium are here. So the first point is the static electric field intensity inside a conductor is always equal to 0. Next to that, the static electric field intensity at the surface of a conductor is everywhere directed normal to that surface, and the conductor surface is an equipotential surface. We have, I suppose, 5th or 6th chapter to be the capacitance, and then the potential concept we have discussed in the static electric field. So whatever the conductive material, it will be there on the body of that particular conductive material. That means the surface area of that particular body will be having the charges if it is provided thereupon, and the potential level will be the same onto the entire surface here. So we have talked about the equipotential surface here. So the formulae we can directly take from where I have derived the boundary conditions for the free space separated from the conductive material medium, and we can solve problems here. Now let us have a recap of the second type of the boundary. So second type of the boundary is the boundary between two perfect dielectric materials here. So as already I discussed that the material can be described by the three parameters: sigma, epsilon, and mu here. As we are talking about the dielectrics here, there it is no magnetism associated to the two material mediums here. So that is why for the mu here, it will be equal to mu 0. So mu 0 is equal to 4 pi into 10 raised to the power minus 7 Henry per meter. Whereas as both are the perfect dielectrics, so that time sigma will also be equal to 0 here. So conductivity is equal to 0. Then the permeability of the medium is equal to mu 0. Only the difference between the two mediums here will be with respect to the epsilon, that it means the permittivity of the material medium here. So here we have denoted the area or the surroundings that is above the line that separates the two. Here it is by region 1, and for the region 1 the permittivity of the medium is denoted by epsilon 1, whereas the region below the line separating the first region from the another part here it is denoted by region 2, and the permittivity of the medium is denoted by epsilon 2 here. So the thing is, sigma is same in both the mediums here. Sigma is equal to 0, and mu, permeability of the medium, is also same. Mu 0 it is there, 4 pi into 10 raised to the power minus 7. Only the change is there in epsilon. So epsilon 1 can be written as epsilon r1 into epsilon 0. So epsilon r1 is the relative permittivity of the region 1, whereas epsilon 2 can also be written as epsilon r2 into epsilon 0. So it is relative permittivity of the region 2 here. So in such a case, the behavior of, again we have to consider only the electric field intensity denoted by capital E and the electric flux density denoted by capital D here. So here we have in this particular diagram the tangential components of the electric field intensity. So E tan 1 means tangential component of electric field intensity into the region 1, whereas E tan 2 is tangential component of electric field intensity into region 2. Similarly, capital N into the suffix denotes it is a normal component, it is a perpendicular. See, this arrow is making 90-degree angle with the boundary separating region 1 from region 2. So dn1 it means normal component of electric flux density into the region 1. dn2 is normal component of electric flux density into the region 2 here. So in this situation we are making the use of a closed loop as shown in this particular diagram. Here we shall have the integration of the E component here, closed line integral E bar dot of dl bar, that we will try to uh, solve here, and whatever the outcome will be there, from that we shall be deciding the behavior of the electric field intensity component, and those particular outcomes we come to see to be the boundary conditions here. Similarly, on to the closed surface here that encloses a certain volume inside. So this is what the closed surface we have shown here. Thereupon we shall have the integration. For example, the closed surface integral of d bar dot of ds bar. That it means how much electric flux is passing from that particular closed surface as per the Gauss's law you can consider. So this is what the second condition. From that we will derive what is the behavior of the electric flux density component here at the boundary separating region 1 from region 2 here. So the thing is very simple. We have to go with our electromagnetic signal from one region to another signal. What changes occur as we cross the boundary, that will be described by the boundary conditions here. And here it is the arrow just describing a perpendicular direction to the boundary here, and the normal it is, and the notation is of course small n here. So for such a boundary that separates the two perfect dielectric materials here, there are certain formulas we have already been derived with. E tan 1 is equal to E tan 2. So tan means tangential component, a parallel component. So according to this relation, electric field intensity in material medium 1 is equal to the tangential component of electric field intensity into the region 2. So it means there is no change into the tangential component of electric as it crosses the boundary that separates the two perfect dielectric materials here. Now here we have another formulation that describes the relationship between the tangential components of the electric flux densities. From the above relation, if you just have the division to the above equation by the corresponding permittivities here. So we have here d tan 1 divided by d tan 2 is equal to epsilon 1 upon epsilon 2 here. So the ratio of tangential component of electric flux density in medium 1 to that of medium 2 is nothing but the ratio of permittivity of the first medium to that of the second medium here. Next to that we have dn1 is minus dn2 is equal to rho s. So if the boundary that separates the two perfect dielectrics possesses certain kind of charge onto the boundary surface, so there it will be the surface charge density denoted by rho s. So as you see onto the RHS here, so that time the difference between the normal components of electric flux density into the region 1 and region 2 will be equal to that rho s. And if there is no charge onto the boundary that separates the two perfect dielectric materials here, so that time we have to put it equal to 0, and dn1 will be equal to dn2 here. So that is the thing that I was talking. Now we have if the change of the vector with respect to the normal, if we have the angle theta, and so that time the electric flux density into the second region will be calculated by using the electric flux density. There it is in the region 1 here, and this is with respect to the angle theta 1 made to that of the normal direction I have shown to you in the preceding illustration here, and of course it depends on the epsilon 2 and epsilon 1 here. Similar is the fashion we are computing the electric field intensity into the second region. E2 is equal to E1 multiplied by the square root of sine square theta 1 added to the square of the ratio epsilon 1 by epsilon 2 into cos theta 1 squared here. So these are the formulae we shall be making the use of for discussing and deriving the things related to the boundary separating the two perfect dielectric material mediums and solving the concerned problems here. Next to that we have the third type of the boundary I just initially introduced you to people. So this is also known to be the magnetic boundary condition. See here, as I discussed, any material medium will have properties described in terms of sigma, epsilon and mu here. So sigma is conductivity and epsilon is permittivity and mu is permeability. So here for the magnetic boundary conditions, the two material mediums are separated by the mu. Permeability is different. For the region 1, here it is by mu 1. For the region 2, here it is by mu 2, and rest of the two parameters are same here. So the behavior of magnetic components I have already talked about, that E and D are correspondingly the electric field intensity and electric flux density, the two components describing the electric field here, and here H describes the magnetic field intensity and B describes the magnetic flux density. So here you see HT1 is the tangential component of magnetic field intensity in the region 1. See its direction, it is parallel to the boundary line that separates the region 1 to region 2. Similarly, HT2 is the tangential component of magnetic field intensity into the region 2. We have BN1, BN1, N in the suffix, it means a normal. B is the magnetic flux density. Magnetic flux density into the region 1, and that is normal to the boundary. So normal component of magnetic flux density in the region 1. Normal component of magnetic flux density into the region 2 here. So with the help of the closed surface and the closed loop like this, we have the analysis of the boundary with respect to the magnetic field intensity and magnetic flux density, taking the closed line integral and the closed surface integral. We get few of the equations, what we call magnetic boundary conditions here. So here we have few of the problems, few of the formulas here. Bn2 is equal to Bn1. So it means normal component of magnetic flux density in region 2 is equal to the normal component of magnetic flux density into the region 1. So no change occurs while the field changes region 1 to region 2 here. Whereas we have the normal component of magnetic field intensity described by the normal component of magnetic field intensity in region 1 multiplied to the ratio of mu1 to mu2. Next to that, we have HT1 minus HT2 is equal to K. See, K is the surface current. When the two regions, the two magnetic regions I say, so the boundary surface that separates the region 1 from region 2, and if that surface is having a surface current, so that time of course there it will be the surface current density here. So this density K is of course always described in terms of ampere per meter here. So how much current is flowing with respect to a line segment, if you have, I have already described it in many of my previous lectures here. From there you can study about this particular parameter here, and if there it is no current component, you can put it equal to 0 here. So converting the above equation with respect to the tangential components of magnetic flux densities, we describe it as Bt1 by mu1 minus Bt2 by mu2, that is equal to K here. So with all these understandings, here we are going to solve few of the problem statements associated to the boundary conditions here. So let us have the first problem statement. So the first problem statement is, the statement starts with, the surface x is equal to 0 separates the two perfect dielectrics. For x greater than 0, let epsilon r is equal to epsilon r1 is equal to 3, while epsilon r2 is equal to 5 where x less than 0. if E1 component is given as 80 AX minus 60 AY minus 30 AZ measured in volts per meter, find the part A. We have to determine En1, part B Et1, part C Et1, part D E1. Then in the E part, the angle theta 1 between E1 and the normal to the surface. Next to that, we require to determine dN2, then dt2, then d2, then p2, and then the angle theta 2 between E2 and normal to the surface here. So this is our problem statement here. We have to solve it. Now we have discussed initially the three types of the boundary conditions here. First it was with the free space and the conductor. Second it was between the two perfect dielectrics, and the third it was the magnetic boundary condition. The magnetic materials were separated by a boundary line here. Now here in the statement you have to identify it is between two perfect dielectrics. So it was of the second number boundary condition that I discussed here. So the corresponding formulae here you have to use, and you have to determine the required components by utilizing the given data in the problem statement here. Now let us imagine what is the condition and what is the situation provided here. The surface is defined by x is equal to 0. See here, generally I am taking the right handed coordinate system, this to be the z axis. This is having the positive z direction values, negative z direction values. Perpendicular to it we have positive y values, negative y values. So these are the two axes in the plane of the digital screen that you are watching, and perpendicular to it, that it means coming towards you and inside the digital device here. So here we have positive x coming out towards you, that is perpendicular to the digital screen, and in the reverse direction negative x here. So when we talk about x is equal to 0, so it means that we have fixed the value of the x, not the y and z. So it is your digital screen. So it is nothing but the yz plane here. So when you have the values x greater than 0, so it means outside the digital screen towards you people, and when it is x less than 0, it is behind the digital screen, inside the digital device here. So as per this problem statement, outside the digital screen the epsilon r is equal to 3, whereas inside the device the epsilon r is equal to 5. So if E1 is given to you, E1 is the electric field intensity vector measured in terms of volts per meter. So here it is the vector described by 80 AX minus 60 AY minus 30 AZ. So from the first chapter you will come to see that AX, AY, AZ are the unit vectors. So it means it is the identification of a rectangular coordinate system for representation of the vectors here. So E1, the electric field intensity in region 1 is given to you. By using this information you have to determine others here. So En1, it means normal component of electric field intensity you have to determine from this information. Then the tangential quantity is also to be determined, both are the vectors here. Then the magnitude of the tangential quantity can to be determined. Then the complete E1 magnitude you have to determine. Similarly rest of the things you have to compute here. So one by one we shall be going for every case here. So here first of all, in part A we require the value of the En1, normal component of electric field intensity in the region 1. So as x is equal to 0 is the boundary, we can obtain En1, normal component of electric field intensity in region 1, just by having dot multiplication to the E1 vector by AX unit vector here. So for part A we write E1 vector dot multiplication with AX vector here, and this value comes out to be 80 volts per meter. So this is the answer for part A. Now in the part B we require ET1 here. So ET1 is the tangential component of the electric field intensity vector quantity in region 1. So this has the components of E1, that is not normal to the surface but tangential to the surface. The surface is x is equal to 0. So the x component will be normal to it, not the y and z. So y and z are the tangential here. So therefore we write ET1 is equal to minus 60 AY minus 30 AZ volts per meter here. So from the given E1 was described to be 80 AX minus 60 AY minus 30 AZ. So the first term has given us the answer here. So as this is the dot multiplication, we have obtained only the magnitude here, not the direction here. And here it is the tangential component by the second and the third term in the description of that electric field intensity vector already given to us in the problem statement. So this is the solution for part A and part B here. Now we have to move on to part C. In the part C we require the magnitude of the tangential component that just now we have computed here. So we have the vector minus 60 AY minus 30 AZ. So its corresponding magnitude will be obtained just by taking square root. Inside the square root we have to make a summation of the squares of the coefficients here. So ET1 will be equal to square root of 60 square plus 30 square. The value comes to be 67.1. As this is the value of electric field intensity, it has to be always measured in terms of volts per meter here. Now in the part D we are required to compute E1 here. So capital E1 is electric field intensity in the region 1. So as we know, this is just the summation of the tangential component and that of the normal component. So here the E1, as we require the magnitude of the same here, so that time we take the square root of E1 vector is given to us in the problem statement. So it is 80 AX minus 60 AY minus 30 AZ here. So in the square root we take the addition of 80 square plus 60 square plus 30 square. The coefficients are to be squared, they have to be summed up, and for this summation the square root is to be determined here. That will provide you the value of the magnitude here. This value comes out to be 104.4. So this is the value, this is the magnitude of electric field intensity. So it has to be represented with the SI system of unit volts per meter here. Now we come to the next part here. So these are the corresponding two solutions for part C and part D that you can outline here. So out of A to J, the first four answers here we have. We go for the fifth one, the E part. We require the angle theta 1 between the vector E1 and the normal to the surface. So for the angle determination, we can make the use of one of the formula that I have already discussed in the beginning here. So cosine of the angle theta 1, if you take, it will be just the ratio of, in the first part we have obtained En1. So that it was by E1 dot multiplied with that of AX, and if it is divided by capital E1, so it is nothing but the cos theta 1 here. So if we have the substitution of the answers from part A and part D, part A answer was 80 volts per meter, part D answer was 104.4 volts per meter. So in the numerator we put 80, in the denominator we put 104.4 here. So from this relation, cosine of theta 1 is equal to this particular ratio. So theta 1 can be determined. We obtain theta 1 is equal to, by the cosine inverse, of course you can do it on your engineering calculator, it is equal to 40 degrees here. So this is what the answer for part E here. Okay. Now we are going to have the solution for part F. In the part F, we require the normal component of electric flux density in the region 2 here. So as per the boundary condition, the normal component of the electric flux density is continuous across the boundary. So it means dN2 is equal to dN1 here. So we require the value of dN1. Have we been provided the value of dN1 in the problem statement? We have not been provided, but we have been provided the value of normal component of electric field intensity. If you have the multiplication of electric field intensity component by the permittivity of the medium, that means epsilon multiplied to Et, so that it will be the electric flux density here. So we have computed En1, so we just have multiplication of that, it is epsilon into En. Epsilon we just split into the two. Epsilon R1 into epsilon 0 is simply the epsilon here. When it is multiplied to En1, we can obtain Dn1 here. So here we can substitute the value. In the problem statement, we have been provided epsilon R1 is equal to 3. Epsilon 0 value is the constant value, very well known to us. It is 8.854 into 10 raised to the power minus 12. And the answer of part A will be En1. So we put epsilon is equal to 3, epsilon 0 is equal to this bracket, 8.85 into 10 raised to the power minus 12, and En1 is equal to 80. So this multiplication will be equal to Dn2. So in the region 2, the normal component of electric flux density is obtained to be 2.12 nanocoulomb per meter square. See, coulomb per meter square is the SI unit to represent electric flux density. Nano is just the multiplicand. Nano is 10 raised to the power minus 9 here. So 2 into 2.12 into 10 raised to the power minus 9 is the answer here. So this answer you can note down. I can outline this particular answer. This is the solution for part F. This is the solution for part E here. Now after this, we are going to have solution for part G. In the part G, we are required to compute dt2 here. So dt2, tangential component of electric flux density into the region 2 here. So do we have this particular component? We don't have this particular component, but we can have the tangential components to be continuous across the boundary for the electric flux density as per the boundary condition between the two perfect dielectrics here. So we can put a dt2 is equal to Et2, dt1 here. dt2 is equal to dt1 here, and dt1 we can express as epsilon into Et1, epsilon as epsilon R2 into epsilon 0 into Et1 here. And if you put the values here for the region 2, we have the permittivity, relative permittivity, that is equal to 5. So 5 into 8.85 into 10 raised to the power minus 12 into Et1. The Et1 value we have derived into the part C. The part C answer, if you substitute in this particular place, that it is 67.1, we obtain the corresponding answer of part G. And here it is 2.97 into 10 raised to the power minus 9 in terms of coulombs per meter square. So here we express it as 2.97 nanocoulomb per meter square. So this is the value of dt2 here. So the solution for part G here. Now in the part H, we are required to compute d2. So d2 is the complete electric flux density vector quantity in the region 2. So if we can have the addition of the normal component and that of the tangential component, so it will be the resultant vector quantity here. But we don't have directly the dt1, dt2 and et2 to here. By using the boundary conditions, we can have the substitutions and make the use as d2 is equal to epsilon r1 into epsilon 0 en1 into ax added by epsilon r2 into epsilon 0 into et1 here. So we have the values to substitute here. So in this particular part here, if we substitute the values of the relative permittivities of the mediums for the region 1 and region 2, the constant 2 times here. So here it will be 3, here it will be 5, epsilon 0 will be 8.854 into 10 to the power minus 12. En1 answer, the vector quantity you can put from the first one here, so that it will be 80 ax, and et1 the tangential component you have the answer from part B, that is minus 60 ay minus 30 az. So the result here we obtain, that is 2.12 ax minus 2.66 ay minus 1.33 az into 10 to the power minus 9, that it is nano. So we have this in terms of nano coulombs per meter square here. So D2 answer here I outline. This is the solution for part H here. So after part H, we require to make computation for part I and part J here. So in the part I, we require the computation of the vector capital P2 here. See, capital P2 is just the difference of the vector D2, that it is the electric field, electric flux density in the region 2, minus the epsilon 0 multiplied to the electric field intensity into the region 2 here. See, this D2 comprises of epsilon R2 into epsilon 0 into E2 here, whereas the second term you see there it is no relative permittivity. So electric flux density into the free space medium and electric flux density into the region 2. From the two we have to take a difference, and that difference is nothing but the P2 here. So here we compute it as P2 is equal to, here D2 we can take out as a constant here, and we shall be left with inside the bracket 1 minus within the parenthesis 1 upon epsilon R2. So if we substitute, we get it to the form 4 by 5 times capital D2, and this vector quantity becomes 1.70 into AX minus 2.13 into AY minus 1.06 into AZ in terms of nanocoulombs per meter square here. So this is what the solution for part I here. So P2 here I outline. This is the answer here. Now there it is the last portion, part J, to be solved here. So for part J, we require the angle theta 2 between E2 and the normal to the surface here. So as like we had the solution for part E, for determination of the angle, we have made the use of the cosine ratio here. So thereupon it was cosine theta 1 equal to E1 dot AX divided by E1 here. So here for cosine of theta 2, as we are in the region 2 here, so for cosine theta 2 we have E2 dot AX divided by E2 here. So as we have the values from the previous FG sections for the normal and the tangential components of electric flux densities, we get this converted to the electric flux density. Just it will be the cancellation of the permittivities of the material mediums into the corresponding regions here. So we get it to the form d2 dot ax divided by capital D2 here. So substitution of the answers from the part F in the numerator we can put 2.12 here. So 2.12 we have been taking from part F here, and if we add it to the portion from part G here, or for the part H, if we can find just the magnitude by taking the square root and summing all the things here, so it will be like this. You see part H answer here, it is 2.12 AX minus 2.66 AY minus 1.33 AZ here. So the coefficient values have been squared here and further added here. So this is just a typo mistake. This should not be a plus sign. this should not be a equal to sign, this should be a plus sign here. So if you substitute all these particular values, you get the value of cosine theta 2 is equal to 0.581, and when you take the inverse cosine, so theta 2 will be equal to cosine inverse of 0.581, and this is equal to 54.5 in terms of degrees here. So this way we have the solution to all the portions, part A, B, C, D, E, F, G, H, I and J. So these many portions we have solved here, and we have obtained the corresponding answers here. Now after this problem number 1 associated to the boundary separating the two perfect dielectric material mediums here, we are going for the another problem again for the two perfect dielectric material medium. So as far as the examination is concerned, more focus is there on the boundary between the two perfect dielectric material medium here. So here we have the problem statement that starts like: two perfect dielectrics have relative permittivities epsilon r1 is equal to 2 and epsilon r2 is equal to 8. The planar interface between them is the surface x minus y plus 2z is equal to 5. The origin lies in region 1. If capital E1 is equal to 100 AX plus 200 AY minus 50 AZ in terms of volts per meter, find capital E2. So this is our problem statement. So if you read this particular problem statement, you will come to see that there it is certain surface defined by this particular equation here. So x minus y plus 2z, this is just the planar interface. Okay, so this is a plane, we have called it to be a planar interface between the two regions, and both the regions are perfect dielectrics. The corresponding epsilon r1 and epsilon r2 are there. So if this is the plane that separates the region 1 from region 2, in the region 1 we have the value of epsilon to be 2 relative, and for the region 2 if it is equal to 8. So here we have epsilon is equal to 2 into epsilon 0, and the epsilon in this particular region is equal to 8 into epsilon 0 here. So this is what the situation. So here it is mentioned that the origin lies into the region 1. Somewhere here it should be the origin O, and if E1 vector is given to us, we have to find E2 vector. The electric field intensity in region 1 is given to us. We have to determine the electric field intensity into the region 2 here. So now for solution to this particular problem, we actually need to find the components of E1 vector, that are whether normal and then further tangential to the boundary that separates the two regions here. Then we have to apply the appropriate boundary condition. The boundary condition between the two perfect dielectric material mediums we have studied. So those relations we can make into use here. So the normal component here, it will be En1. It will be denoted by En1 here. So En1 can be just obtained by having the dot multiplication to the E1 vector given by the n vector. N is the perpendicular direction to the boundary surface here. So if here we take f is equal to x minus y plus 2z, that is the planar interface between the two regions here, the unit vector that is normal to the surface we can obtain as, here we have delta f divided by the del f magnitude here. So this is equal to 1 upon under root 6. In the square bracket we have the unit vectors ax minus ay plus twice az. So this particular n, the n that you see, This is the normal, and this will point in the direction of increasing the F. Increasing the F means the planar interface here. So this will be away from the origin or into the region 2. So for example, if we can visualize the portion of the surface as a triangle whose vertices are on the 3 coordinate axes as x is equal to 5, y is equal to minus 5 and z is equal to 2.5. So that time you will come to have the visualization here. So if we have the normal component of the electric field intensity into the region 1 to be like from the above equation 1 upon under root 6 multiplied 2, inside the bracket we have 100 minus 200 minus 100, and this value comes out to be minus 81.7 volts per meter here. So we require the complete E2 here, and here we have the normal component of electric field intensity into the region 1. Now since the magnitude here we have in negative, the normal component points into the region 1 from the surface. So therefore we write En1 is equal to minus 81.65 multiplied to 1 upon under root 6, the ratio multiplied to the square bracket that holds Ax minus Ay plus twice Az. The bracket is completed here. So this is equal to, in the vector form we have minus 33.33 Ax added to positive 33.33 Ay minus 66.67 Az in terms of volts per meter. So now the tangential component from this particular equation we can find out, that is Et1 is equal to E1 minus normal component En1. So En1 we have already written. So here it will be 133.3 Ax plus 166.7 Ay plus 16.67 Az here. Now according to the boundary condition, Et2 is equal to Et1 and En2 can be obtained as we have epsilon R1 upon epsilon R2 multiplied to En1. So this becomes 1 upon 4 En1 here, because in the problem statement the epsilon R1 is equal to 2, epsilon R2 is equal to 8. So 2 by 8 is nothing but 1 by 4 here. So therefore we require the complete electric field intensity into the region 2, that it is E2, that is the addition of the corresponding tangential component and normal component of electric field intensity, of course, into the region 2. So here from the boundary condition we make the substitution. For the first term there it is Et1, and for the second term we have 1 by 4 times En1 here. So now Et1 we have, En1 also we have. So making the substitutions, the E2 expression becomes 133.3 Ax added to 166.7 Ay plus 16.67 Az minus 8.3 Ax plus 8.3 Ay minus 16.67 Az here. Now we have to add the similar kind of the terms from this particular right hand side. Whatever the coefficients of the Ax here we have, that we can club together, whether it is addition or the subtraction. So thereupon we come to have the E2 vector to be 125 times Ax added by 175 times Ay here. Now you see the Az component, that it was positive 16.67 Az and negative 16.67 Az. So these will be cancelled out because the coefficient is having the same value, and once there it is positive, another there it is a negative, the subtraction will result into 0 times Az here. Whereas from 133.3 we can subtract 8.3 and we can obtain 125 here. From 166.7 we can add 8.3, it becomes 175 here. So this way we have the corresponding answer for the vector E2 here. So this is what the solution to the second problem we have dealt here. So this way we have a practice of the two problems. Those both we have taken from the two perfect dielectric separated by a boundary surface here, and this was really very interesting topic. We had the we had the three types of the boundary conditions. As far as the examination is there, more focus is there on the boundary between the two perfect material mediums here. Also onto the magnetic boundary conditions, you can have the various type of the problems, those you can solve with whatever the formula I have shown to you. And of course it will be with respect to the H describing the magnetic field intensity, and B describing the magnetic flux density in the very similar manner as we have for the E describing electric field intensity, and capital D describing electric flux density. For more details, you can attend my lectures. Those are already available on the online platform of Ekeeda. Thank you.